Have you ever actually stopped to think about what's directly beneath your feet? We spend so much of our time looking up at the sun and the wind for renewable energy, but what if the ultimate, continuous power source is sitting right under us, just waiting to be tapped?
Welcome to this explainer. Today, we're going on a trip, literally, from the core to the current to demystify geothermal energy. The sheer scale and, frankly, the ingenuity of this technology are absolutely fascinating. And it's a power source we actually rely on way more than you might think.
So, here is our roadmap for today. We'll be looking at the Earth's hidden heat, direct heating and cooling, ground source heat pumps, and finally, generating geothermal electricity. Let's dive right in.
Section 1. The Earth's hidden heat, our radioactive boiler.
Okay, to understand exactly where all this immense power comes from, we really have to start at the very center of our planet. The Earth's core is about 6,500 kilometers deep, and get this, it's actually as hot as the surface of the sun. It acts like a massive, almost unimaginable boiler. The temperature in the magma stays incredibly high, primarily because of the continuous decay of radioactive particles. That heat then transfers outward through the mantle, warming up rocks and underground water near the crust, and that right there is the energy we want to capture.
Now, scientists generally break these geothermal resources down into four main buckets: hydrothermal, geopressurized, magma, and enhanced systems. But here's the absolutely key takeaway. Right now, with our current technology, we really only exploit the natural high-temperature hydrothermal resources. The other three, they have enormous energy potential for sure, but they remain largely untapped frontiers for future engineers to figure out.
But even within those hydrothermal resources we do use, the temperature basically dictates everything about how we apply it. High-temperature resources, so anything over 150 degrees Celsius, those are the heavy hitters. We use them for generating massive amounts of electricity. On the flip side, your lower-temperature resources, the ones under 90 degrees Celsius, those are absolutely perfect for local space heating. So there's a really clear line between massive grid-level power generation and just keeping your house warm on a Tuesday. Which brings us to Section 2, direct heating and cooling, bringing the heat home. Let's zoom back up to the surface for a second and see how lower temperature resources are utilized directly for our physical comfort. In places like Iceland, nearly 90% of buildings are heated directly by geothermal heat in the winter. It's incredible, but there is a bit of a catch. Geothermal brine can be highly corrosive and packed with dissolved solids. I mean, you definitely can't just pump that directly into someone's living room radiator. So district heating systems use heat exchangers. The hot, corrosive geothermal fluid heats up fresh water safely across a physical barrier, and then that heated fresh water is what actually gets pumped into people's homes. It's just a brilliantly elegant solution that saves immense natural gas costs.
Section 3. Ground source heat pumps, the efficiency secret.
But hey, what if you don't happen to live right next to a bubbling hot spring? Well, let's zoom into our own everyday backyards. You see, the weather above ground fluctuates wildly. We all know that. But if you dig down just below 10 meters, the ground temperature stays remarkably stable all year round. It's noticeably warmer than the freezing winter air and much cooler than the sweltering summer air. So the core advantage here is that the Earth essentially acts as a perfectly stable heat source in the winter and a heat sink in the summer.
So the crucial point becomes, how do we actually measure the efficiency of capturing this stable temperature? That brings us to the coefficient of performance, or COP. The COP is basically just the ratio of useful heating or cooling provided to the electrical work required to run the pump. Because these systems are merely moving heat from the stable ground into your house, rather than, generating heat by burning fuel, they achieve insanely high COPs. And practically speaking, this means these pumps save actual hard dollars on your heating bills.
Now, how you extract this shallow heat depends entirely on the real estate you have available to work with. There are three main piping configurations. A horizontal loop requires a relatively large backyard for digging shallow trenches. A vertical loop, or a borehole, drills straight down, which is absolutely perfect if you're working with smaller spaces. And finally, groundwater wells circulate actual underground water right through the system. It's highly adaptable engineering that brings the Earth's stable temperatures right into our homes.
Section 4. Generating geothermal electricity, powering the grid.
All right, let's zoom way back out to a massive scale to see how those high-temperature resources we talked about are engineered into actual baseload electricity. Just to give you an idea of the sheer scale we're talking about here, the United States alone generates a whopping 3,550 megawatts of geothermal electricity. That is serious, continuous baseload power running day and night, regardless of whether the sun is shining or the wind is blowing. And here is the wild part. You don't always need boiling magma to achieve this. We have real-world, small-scale power plants operating right now in places like Nevada. They successfully generate power from a relatively low 120 degrees Celsius liquid resource. It's amazing proof that with the right engineering, electricity can be generated from remarkably modest geothermal liquid temperatures.
So, how do the most common types of plants actually operate? Let's talk about the single-flash geothermal power plant. Interestingly enough, we are actually pulling up high-pressure liquid water from the earth here, not steam. The secret to making the turbine spin all comes down to a sudden change in pressure. Let me show you how that works.
Without getting totally bogged down in complex thermodynamics, it's actually a beautifully simple process. Step 1. The hot, high-pressure liquid enters a flash chamber. Step 2. The pressure inside that chamber is suddenly dropped. Boom! This causes a portion of the liquid to instantly flash, or basically boil rapidly, straight into steam. And step 3, that powerful steam is separated off and routed directly to drive the turbine, while the leftover liquid is just safely re-injected back into the earth.
But wait, what if that water just isn't quite hot enough to flash into steam efficiently? That's where we bring in the binary cycle power plant. Instead of trying to flash the geothermal water, we use it to heat up a secondary chemical fluid, something like isobutane or pentane, which naturally has a much lower boiling point. The geothermal heat boils this secondary fluid into a vapor, and that vapor is what drives the turbine. The two liquids never even touch. It's a completely closed loop.
And you know what? We can actually combine the best of both worlds with a hybrid flash binary plant. It maximizes efficiency by first flashing the hottest water into steam to turn one turbine, and then taking the leftover liquid that wasn't quite hot enough to flash and routing it right through a binary cycle to turn a second turbine. It perfectly cascades the energy. They are literally squeezing every last drop out of the resource.
When you look at the global breakdown of plant types today, the single-flash plant overwhelmingly dominates the worldwide market. That's followed by dry steam, double flash, and finally binary systems. It's a highly developed, mature set of technologies.
But here's the really big takeaway from all of this. Remember, we are currently only exploiting natural hydrothermal resources, with massive reservoirs of magma and completely untouched enhanced hot dry rock systems waiting right down there beneath our feet. What is the true limit of our planet's power? It is a massive, wide-open frontier of future engineering. Thank you so much for joining me on this explainer. I really hope you found this core-to-current journey as mind-blowing as I do.